exoplanetary science, most of these three examples. And if time permits, then I'll also talk about something on protoplanetary disk or astrochemistry. So these are the like overall the topic in which I'm working right now as a part of our institute projects. And since these are very different topics, so for today's talk, I'll try to give a very brief overview of some examples how these different topics actually connected through machine learning. And then I'm really sorry that I'll not able to go through the way details of all these different topic. What I'll do, I'll prepare the slide in a way that like I can present individual examples and then show how where we actually this on this context. Um, I'll start with the example for the space technology, and then I'll start with very non-scientific project, which is basically our one of our institute project, which we are talking about how to develop local large language model. And you know, these days local large language models is very very popular. And now we have a lot of different company which companies are already developing this kind of model, right? For example, OpenAI developed Chat GPT model, then Llama model developed by Meta, then DeepSeek by DeepSeek company, then Quen from Alibaba, then Grok from Elon Musk, and then also Gemini from Google. So these are the different popular models, and normally the way we are using these models more like as a user. So whenever we are actually using this model, is basically we are connected through some API web server to those kind of model directly, and then we are asking some questions to this kind of model, and we are getting some answers. See, since these models are already trained on very large online available data set, therefore these models can answer different type of questions in the context of different data, right? But what if we really want to use this kind of model for some confidential data? So when I'm saying confidential data, is basically I'm considering that confidential data is nothing but the local data, which is basically access to us only. And we really want to see that like can we design some kind of local large language model with our own data, and that I'm defining as a domain knowledge. Two possibility to develop this kind of local large language model. One is basically the TDS method is basically to fine tune this kind of model. So you can download these models and then you can try to fine tune with your domain specific data. So of course, if your domain specific data, if it's very large data, then basically the fine tuning of a model, it took a lot of time. Therefore, it is very difficult to do a fine tuning. Normally, it can work with domain specific data with size of small or moderate size, where you can free some of the layers and then try to fine tune again some new weights, and then see that like how those weights distributions actually changing with your data, and that could be one option. But this, as I said, like this needs a very big cluster, because these models are having billions of parameters. Therefore, to load the model and also to train the model with new data would take a lot of time. So what are the other alternative options could be? So option two is basically try to not to train the model, rather than give the model a context. So that I'm defining as a knowledge expansion. So what you can do, think about that normally when you're asking some questions to the model, it gives the answer directly. Whereas what you can do that rather than directly passing that query to the model, we can design our own database set of kind of setup where we can provide our domain knowledge. For example, IWF is basically our institute. It's like institution of Wellcome Forschung. So then our institute having our own domain knowledge, and then we try to give that domain knowledge or integrate that domain knowledge to the model in a way that like whenever the user is making a query, we can do a search based on our domain knowledge. That means basically if the query is related to some specific topic on our data, then the model should first go to this database and try to understand what is the context of the problem or the query. Once you understand that context, you can retrieve that information, and then you can do the knowledge expansion. Basically, then you have the query, and then you will get some kind of new information from your own database, and that information you can pass as extra information to the model, and then the model can prepare a new answer with this knowledge expansion, and that could be your new answer. So therefore, in this way, you can actually reduce the training thing, because you are not doing the proper training. What you are doing, you are making a sort of a database representation of your own data, and then you're connecting that through your query, and then the model can actually get back the solution on that. So this setup is very known popular in this domain, that is called retrieval augmented generative model, that is called RAG. And we have developed our own RAG setup. And why you are interested to do this kind of exercise? So basically, our Spaces Institute actually involved in lot of ESA missions, and we have our own lot of confidential data, and also as well as code. So we really want to develop our own local writing assistant and coding assistant, which may not be directly available to the which is basically connecting through this data which are not directly available or publicly available in the internet. So practically, we have now our own local installed large language model, modified version in terms of this kind of connected to this kind of RAG setup in our local cluster, and then we are providing that to a service to our engineers. So therefore, we have our local server where they can access to these four models right now: the Llama, Mistral, and Qwen, and DeepSeek, and which are also connected with our own database. And therefore, it is I would say it's the local version of the same language model, but it can answer to our queries. So this is the one example which is non-scientific in that sense, but for the engineering department, it is very useful in terms of because they need to prepare a lot of documentation, as well as they need to do a lot of coding debug. So therefore, that is good for them to have this kind of tool. Second example for space technology, normally we are talking about space debris. So we are talking about, whenever we are talking about we have our satellite disarranging group, and we are actually talking about how to classify these kind of different kind of space debris representation through this photon light curves. So when I'm talking about light curves, basically light curves actually are very noisy representation of you can say the reflection of the sunlight or the satellite and debris, and this kind of representation we are getting we are collecting from in our observatory. So normally what you need to do, for different light curve, we have a different signature in terms of the debris representation, or you can so we need to connect this kind of representation with the light curves and try to see that, like, can we design some kind of a classifier method which could actually understand what kind of shapes are actually connected through this light curve. So basically, we are trying to predict this kind of shape from the light curve representation. But the practical problem is that, like, these light curves are very, very noisy, and it is very difficult to design some machine learning model which can directly learn from this kind of data representation. So what we did, we actually converted the data into some feature representation, and then we trained a CNN architecture which can actually learn about this kind of shape. And then we for our different kind of shapes, for example, sphere, topics, GLONASS, JSON, and Atlas, these are different kind of space debris shape. Our accuracy of the model is 88% correct, and this one is already published this year. So this is sort of a example of a science engineering department where they can design the data analysis pipeline through this machine learning model, and then that could be useful for their data analysis. Now, coming back to gravitational astronomy, I'll coming back and forth in between these topics. So I'll start with again some basic example of gravitational astronomy where the machine learning could be useful. So one of the project which we did last year is more on the prediction of orchestration, the characterization of the binary black hole system using neural network, in which we are talking about how the signals or gravitational signals looks like when you're talking about the aligned system and when you're talking about the precision system. So when you're talking about the aligned system, we are actually assuming that the masses and the orbital angular momentum is actually is parallel to the spin component that is represented by S1 and S2 here. Whereas when you're talking about the precision system, we are talking that like the orbital angular moment is not aligned with your spin component, and therefore, if you look into the signals morphology, you can expect that the signal morphology could be different for the precision system. And practically, if you think about this, basically a gradual progression on your frequency and amplitude, whereas here is like the amplitude is varying depending on different angle between the orbital angular momentum and the spins. So therefore, identifying these signals from precision or from aligned is an important task, and we have a classical or match filter based method where we can actually identify this kind of precision system. Our aim is to identify, can we design the same problem or solve the same problem using the machine learning setup. And therefore, the basic setup we can think about is a multi-class classification context, where we can think about with the background data. The class 0 is background data is completely noise, background noise, whereas the class 1 is nothing but the signal from aligned system, and class 2 is basically signal from precision system. So this is the way you can design the multi-detector or multi-classification setup. Whereas this is multi-level classification setup, whereas you can also think about that converting this into a two binary classification problem, where the first part would be the binary classification in the context of pure noise versus noisy signal, and noisy signal could contain aligned and precision. So that means basically this is simpler. You can think about this with the simple binary classification between pure noise and signal, and we are not at all considering either it is actually aligned signal or precision signal, but we are actually train the model with all these different signals. Once this model is trained, then we have another binary classification which basically try to classify between the noisy aligned and the noisy precision, and that is another machine learning model. And this model actually only track the training data in terms of aligned, noisy aligned signals and noisy precision signals, and try to see that like once you get back the actual signal from your first classification, pass that data to the second classifier, and then second classifier can predict what is your aligned or precision setup. So we actually perform this hierarchical binary classification and this multi-level classification on our data, and we found that like hierarchical binary classification's accuracy is much higher than the, or moderately higher than the multi-level classification. So practically, we already looked into that too. What if we actually use this kind of model to predict on the real GW event data, and we actually went through all the different events which are available in the first observational run, second observational, and third observational run, and try to estimate or try to predict either it is actually a aligned signal or precision signal, depending on the way we design this model hierarchical binary classification setup. We found that in the first observation run, most so this blue color shows basically it actually matches the way it is reported in the literature, whereas one of them is not matched properly. For the second observation run, also we identified most of this event in the right way. Two of them is not actually aligned the way it is reported earlier. So these are the sort of a representation of the same data set in a machine learning setup to detect either it's a precision or aligned signal. Right now, I think the limitation is that like for few of them is like though it is L1 is saying precision, the H1 is saying, or the second detector is saying this is aligned. So therefore, how to actually identify that it is actually right information or it is actually wrong information, that is one thing which is the current limitation of this model. Possible solution could be that because we know that like the L1 detector is more sensitive, so maybe the results could be weighted more on that information, and that could be considered as the best solution. So this is one example where this kind of model could be useful. Second project where we are talking about basically to design a neural network emulator using gravitational astronomy or for gravitational waveform. I'll start with some revisiting of our previous work where we are talking about classical method, and then I'll show that how this classical method is connected with the machine learning method. So normally when you talk, if you really want to design some fast waveform generation kind of setup. So we already have a one paper where we did the fast waveform generation using the mesh-free approximation. So I'll slightly go through this approach shortly. So what we need to do is, like, for a given signals, you can actually estimate what is the amplitude and the frequency, or the phase. So once you know the amplitude and the frequency or phase, so what you can do, you can actually interpolate those amplitude and the frequency. So to do that interpolation, we actually use this method which is called mesh-free method. And the mesh-free method is basically relying on two different approach. One is singular value decomposition and one is radial basis function. So what we did, we actually fixed the parameter space, or even the boundary of the parameter space, and then we generate a minimal number of nodes, which is basically defining as a RBF, radial basis function nodes, because we need to use RBF interpolation to do that. And then we stack the amplitude and the frequency for two different matrices, and then we actually decompose that matrices in terms of singular value decomposition. And then basically, then the SVD is basically this, you can say the basis vectors are spanning the entire space. They predict the amplitude in the phase with respect to that same basis vector. That means basically the new thing you need to estimate, that is the coefficient. That means basically when you're talking about the amplitude of for a new query point, or the phase for the new query point, you need to estimate the coefficient only for these two, for the amplitude and for the phase. And whereas the basis vector which you obtain from the given nodes are actually fixed. So if you're able to estimate these coefficients through our radial basis function, then basically it is done, and then you can estimate or you can get the good predictions of your waveform. The same approach can be replaced, if that means basically rather than using the RBF method to do this interpolation to estimate the coefficients, you can use the simple, you can say, multi-layer perceptron or deep neural network model to estimate the coefficient. So basically this is actually connecting your mass and spin component, whereas it is basically the aligned spin system. That's why mass 1, mass 2, and the z component. And then you can estimate basically the real and imaginary part in terms of the coefficients. And that's the way you can replace the RBF into the machine learning model. And that is sort of the representation which you can use as a first alternative to the classical method. Second alternative could be that, okay, rather than going for the SVT based basis representation, that is basically the basis representation, nothing but a low dimensional representation, you can actually use a neural network model which is basically called autoencoder or variation autoencoder. They are very similar kind of family of model, where you can actually use the actual data or even actual waveform to reconstruct through sort of a latent space representation, and that could be used as your new data representation. That means basically you are passing your waveform, actual waveform, and you are reconstructing the waveform through a latent space or low dimensional data representation, and then that low dimensional data representation could be used or could be mapped to your given input parameter, and that's the way you can connect them. So this is like basically the simple way to replace the SVT part of alternative to the SVT part of your classical setup. So if I summarize the entire thing, then you can think about, in the classical setup we have a singular decomposition and the radial basis function, whereas in the machine learning setup we already have a similar kind of setup that we can replace the RVF with the multi-layer perceptron, or you can replace the SVT with autoencoder or the variational autoencoder. So if I use this kind of setup, I can also solve the same problem, considering the fact that, okay, input is basically the masses and the spins, and then basically I have one neural network to represent the amplitude predictor, and the another branch could be the phase predictor, and then these two models can directly predict for a given input, and then you can predict the amplitude and the phase. So for this kind of setup, you can use any of this model. Practically, if you directly using the MLP, it could be faster, because you are just calculating the coefficients in a very efficient way. But if you really want to use the autoencoder, variation encoder, the training time would be higher. So it depends on that what kind of parameter space you're talking about, and what data set you are actually used to train or are using to train the model. Then basically based on that you can actually change the setup. So this setups people are using in this domain, and I'm also using a similar kind of setup right now. Sorry, just tell me if I had few minutes. I don't know how much time I have. I hope I have some times, right?
You have total 11 minutes including questions.
Oh, okay, thank you. So I think I have enough time then. So this setup could be used for different kind of
11 questions.
waveform model, and
Can I ask a
the lot
question?
of papers are already you can see in the literature we're talking people talking about different waveform modeling or surrogate representation of this kind of model through for numerical related waveform for other waveform model. So I'm
Please,
also doing the
actually,
similar kind of setup
there is a question.
with a specific model that's called two harmonic. Yeah.
Wait, go ahead.
Sorry, quick question. On the previous slide,
Yeah.
where you show the use of radial basis functions and multi-layer perceptrons, they are acting
Mhm.
effectively as interpolants in high-dimensional spaces, right?
Yes.
Can you comment on whether they perform better or worse than other methods like Gaussian process regression? Are they more compact for
See,
the same amount, same
See,
accuracy?
I would say that, like, I would say the Gaussian process regression has some limitation, right? Because first of all, you need to you need to find the right combination of training data set, right? Because you need to choose the nodes in a way that like the model can learn better, right? Whereas if you choose this kind of setup where you are not at all interested in to predict the entire waveform, but you just want to predict the coefficients, right? Because you already have the basis vector obtained from the SVD, then this model is much easier to predict the waveform. So I would say this setup is then better than the Gaussian process regression.
Will it end up using more flops at the end at evaluation time than GPR?
Sorry, can you repeat your question?
Will it end up using more floating point operations per second or floating point operations
Yes.
at evaluation time than
Training would be,
GPR?
yes, training would
At
be very,
evaluation
very
time.
expensive. That is true because you need more data set, right? So
No,
I
no,
think I
at
forgot to
evaluation time,
explain that
not at training time.
training time. Your prediction will be fast if you are using less number of layers, right? So your floating point operation depending on how many trainable parameter you have in that model, right? So if your model doesn't have more than 2, 3, 4 layers, right? Then I think then it is very fast in terms of prediction, right? Whereas to train the model, it takes time because you are actually using a lot of data set to train the model, right? So that is the one difference between the classical setup and the machine learning setup. Because in classical setup, if I said like the second part, I said like we need minimum number of nodes because you need to perform the SVT. Whereas when you're talking about the machine learning model, we are actually fixing the space or make the boundary, and then we are generating those training data set randomly, right? So basically, you need to space that, or you need to span. We need to you need to choose a lot of data set to train the model. So training would be, of course, very time consuming. Whereas once the model is trained with limited number of layers, then I think it is faster, but of course it is not faster than GPR. So if you're comparing the floating point operation between GPR and this kind of architecture, then of course GPR is faster. I hope I answered your question,
Yeah,
right?
thanks. Yes,
So I'm more interested to because I'm right now working on more on the precision setup. So we have two harmonic representation of precision signals where we are actually assuming that like the precision signals can be simplified or decomposed into a power series based on the given a parameter. That parameter is actually depending on some opening angle, and then opening angle between the orbital and the angular momentum. And if you do that decomposition, basically you are actually getting a precision signal is nothing but linear combination of all five harmonic that is defined as 0, 1, 2, 3, 4, and these are nothing but very linear, or you can say the patterns are basically similar to the aligned signals. So if you look into this plot, it shows basically the different harmonic. The blue is the first harmonic and the orange is the second harmonic. Their behavior is very, very similar to the aligned system. And when you are actually taking all the harmonic together as in terms of the superposition, then basically you are actually obtain the precessing behavior of the signal. So therefore this is very important, or it is very useful to use or decompose any precessing signals in terms of this harmonic, and then obtain, or you can do the match filtering, or you can go for the search and also do the parameter estimation through this kind of setup. But practically to generate this kind of harmonic, you so normally in general for any of this combination of the precessing signals you can use the first two harmonic, but practically you need for all the five harmonic. So now the question is that, like, these models actually takes lot of time to generate, or if you want to generate this kind of signals, then or through this kind of harmonic representation, then of course you're training or when you're running the P, then it takes a lot of time. So we are interested to understand, can we actually represent this harmonic with the same way, the way I showed in the previous slide, through this machine learning emulator representation, and then if it is possible, then basically use that as an alternative or a surrogate to this kind of harmonic representation. So right now I'm working on this project, and the preliminary result shows that, like, when actually I design architecture in a way that, like, all the harmonics could be predicted through this machine learning model, then the predictions are accuracy high, though I have not sampled a very large number of data point right now. So I'm calculating the match between the two signals and the predictor signals through the neural network model, and it shows that the match is actually almost in between the range of point, like 0.99 to in that range. And it shows that basically that, like, this kind of models or the waveforms can also be generated through this kind of neural network model. Okay, so now I'm going to turn to another example, which is basically on the exoplanet climate and weather. Normally, when you're talking about the exoplanet climate and weather, basically we're interested to understand how to do the atmospheric modeling. And why it is important? Because we are actually, when you're talking about the exoplanet, we try to understand the chemistry and try to understand that if there is any signature of life is present in the atmosphere or not, and that basically through the chemical or you can say chemical analysis. So practically, when we're talking about exoplanet or atmosphere modeling, we have to do a classical setup. We have a lot of different components, and the main three components are basically thermohydrodynamics, where it's talking about 3D atmosphere simulation. Basically, you try to make a 3D simulation where you want to see that the temperature difference between the evening and the morning terminator, and then you want to do the cloud formation for the same kind of setup, and then you want to do the additive transfer. Right now, we try to understand that how we can actually replace this kind of in a classical block, because it actually having a lot of computational burden in terms of solving classical equations. And can we actually develop some kind of neural network emulator for this kind of thermohydrodynamics 3D GCM model, and as well as for the cloud formation model? So practically, we successfully developed a model which can actually represent the 3D GCM. And also we have another model which we are defining as a latent space regressor that could actually solve the cloud formation problem. So the problem with the cloud formation is mainly that, like, the different profile, the different temperature pressure profile having a different length. So therefore handling different length with same kind of model would be difficult. And therefore we are actually developed a model where we can actually go through the latent space of a low dimensional representation, and then do all the prediction there. So of course I'll not talk about everything here, but I'll just give a one simple overview of the first problem. So we are
in a minute, if you can wrap up now, in a minute or two, the time is almost up.
Yeah, sure. I think I have these two slides, so I'll just finish it now. Okay, then I think I'll not then go through these slides, because then it will take more time. But practically, you can actually do the similar kind of similar similar kind of emulator the way I showed for the waveform generation. And thank you for this invitation. I would like to thank Chandrakant and Prayush for this invitation, and also thank you audience for listening to this talk. I would like to acknowledge, because it is not like I have done all this work. I have done all this work with the collaboration of a lot of my colleagues and also supervisors. So I'd like to acknowledge all of my collaborators and co-authors. and I'm happy to collaborate if you really want to collaborate some point. So thank you for this.